вот так вот и да, сейчас давай я себя переменю. Все, теперь не подписано. Максим.
Hello everyone. Let us wait 3 minutes. Maybe somebody joined us. Okay, let's start today's seminar. I think you hear me well. If no, or if you have questions, you may use the chat section to give me questions or some comments. My name is Maxim Deminsky, and today I will present a lecture devoted to the simulation of non-equilibrium chemical active plasma with help of the Chemical Workbench code. My suggestion to have this lecture in a live format, so you may give me in any time questions. Probably it will be very helpful for me because I will understand where I can give more detail or where section is not so interesting for you. So okay, well, so in accordance to this item, I will speak about the application of Chemical Workbench for simulation. Probably this code is known for you, or maybe not. But in the beginning, I would like to say several words about the code itself, make some introduction to that. On this slide, you see outline of today's lecture. So we will start from the short description of the Chemical Workbench. And after that, we go more deeper to our particular problem. So we started from the enumeration of the problem when we are trying to elaborate plasma chemical model. After that, we pay attention for collection of plasma model, which we have inside of our code, and the coupling of the plasma model with another model. Another section will be devoted to the data which needed for simulation. How the construction, how we may construct the plasma chemical mechanism, how we may recover unknown data. And in the end of the lecture, there are short two examples will be demonstrated. One is devoted to the modeling of mercury-free line sources, and as another, the modeling of the plasma-assisted combustion. Okay. So several words about the Chemical Workbench code. Actually, it is not a single code, it's environment for the modeling. And this environment consists roughly from the three principal parts. The Chemical Workbench itself, database of the substances properties and the kinetic properties, and chimera code for recovering of unknown data and transform this data to the kinetic database and to Chemical Workbench. This is a general structure of Chemical Workbench environment. So every part is devoted to the following. The Chemical Workbench is a special environment for development and reduction of the chemical mechanism and conceptual design of chemistry-intensive process. Chimera is, as I said, a tool for calculation of microscopic parameters and properties of the elementary process, like the interaction of the heavy particles, or interaction of electron with molecules and atoms. And in database where all properties thermodynamical and kinetical are stored and can be transferred to the Chemical Workbench. About the Chemical Workbench, several words. This code is, as I said, mainly chemically oriented. So it's devoted to the simulation of the process where chemistry is very important. That's why the modeling of the another process, like the mass transfer due to hydrodynamics, realized in the rather simple manner. I will say several words about that later. This code is, can be used in different areas like the combustion, plasma chemistry, pollution control, and other stuff where the chemistry is a key factor for the simulation. Now, deeper in our problem. When we are trying to elaborate some model for the plasma chemistry, we have principal two areas for investigation. The first, left side of this picture, we need to choose an appropriate model. And in our important section, we need to collect all necessary data for simulation. Roughly speaking, we speak about the mechanism. Mechanism means the collection of the thermodynamic, kinetic, and the transport data, all necessary for simulation. The model, when we work about the appropriate model, we're looking for the adequacy of the model to the discharge type. This model should be coupling inside of the electric network, and of course we work about not only about the plasma process, but all plasma process should be coupled with the chemistry. On this slide you see set of the model inside of the chemical workbench. You see, in terms of the hydrodynamics, it's a very simple model, like the well-stirred reactor, plug flow, calorimetric bomb reactor, model which permit to make sensitivity analysis, and the premixed flame model. Of course, we have a set of the thermodynamic model. The calculation equilibrium relies by the two approaches. One, the stoichiometric equilibrium reactor, when the equilibrium established by the set of the equation, balance equation, and as another approach relies through the minimization of the Gibbs potential. About the plasma model, I will say more detail on the next slide. And we have a set of the novel model devoted to the detonation and the others. Okay, so first of all, I should say about what we may expect from this model. Which process taken into account inside and which not. So from the left side, you see which we have and what we can simulate in with the model, and from right what can be done. So all the plasma model in the chemical workbench is a 0D model, or 0D model with some extension in terms of the diffusion to the wall. So it is not 2D or 3-dimensional model. Hence, this model supports uniform values, so uniform distribution of the temperature, pressure, electric fields, concentration, and others. Well, so there is no solution of Navier-Stokes equation. All model working in the approach that plasma and chemical time is much lesser than all hydrodynamics time. But one is the principal advantages of the model is close coupling between the electron distribution function solution with the chemical reaction. Thus, chemical workbench model is elaborated for investigation of the plasma chemical kinetic mechanism and conceptual design of complex chemically active plasma system. From one side, this is advantages of this model. From other side, this is disadvantages. Advantages because this model permits to investigate very detailed mechanism with 1,000 process, with take account of the plasma process, like the interaction with electron, and with using of the very detailed chemical mechanism. Disadvantages, of course, because it's a 0D model and no real hydrodynamics, So this model uses a very simple approach for the hydrodynamic, like I said, perfectly stirred reactor, plug flow reactor, and the other type of the very simple model. These slides show how solution, when we have close coupling between the EDF and the balance for chemical species are found. So as a first step, we solve a Boltzmann equation. In this equation, we take into account all possible processes with participation of the electron. So this is elastic collision, rotational excitation, inelastic collision, so like the dissociation by electron impact, like the excitation of electronic level, superelastic collision, attachment of electron, and electron-electron collision. After the solution as a first step of the Boltzmann equation, we may calculate rate constant, which after that is used in the balance equation for chemical species concentration. After the solution and changing on the first step concentration of the species, we're looking about the condition. Does the concentration change a lot, or another parameter like the pressure temperature, or not? Independent of the changes of this parameter, we may go to the next iterative step with the solution of Boltzmann equation if it's necessary. This is roughly well how to find solution. So more deeply about the plasma model, which relies inside of the chemical workbench. Actually, you may find this model. Sorry, I will open the chemical workbench. I'll try to open this one. Okay. Here, there is a tree of the models which can be used by the user here. So if we're looking for the plasma models, you see there is a many types and the subtypes for of the model which can be used. Okay, so what happened with my presentation? Let me return to this slide. Okay, well, so all plasma model relies through the colorimetric bomb reactor, so it's a model of the closed volume, zero-dimensional and uniform, but time-dependent model. The letters like the P, Q, V, T here, which you can see in the tree, means a different type and condition. P means that pressure is a constant inside of the model. T means that temperature is a constant inside of the model. Also, the additional possibility, if you know how the temperature depends from the temperature, you can use this dependence inside of the model. So, for example, you know the dependence temperature from the time from the experiment. You may calculate in the closed volume, not the pressure constant, but the volume is a constant. Volume also can be changed versus the time, if you know. And also another calculation, adiabatic calculation. So it's opposite to the case of the constant temperature. Adiabatic, it means that, for example, energy which released due to the chemical reaction will lead to the increasing of the enthalpy of the system. Also, there are possibility for variation of the heat exchange between this reactor with the surrounding media, if you know. Also, here you see another set of the plasma model with the surface. This model are very similar to the previous one, but the additional possibility here taken into account is a reaction between the gas species with the surface and reaction of the species on the surface. So this model is very similar to the previous one. but the reaction between the gas and surface species um, take into account through the surface side formalism, when all surfaces are separated by the active and non-active sides, and there are additional equation for the active and non-active side concentration. So there is a possibility to take into account diffusion of the species from the gas to the surface, reaction between them, reaction between the surface species on the surface, or moreover, there possibility for reaction between the surface species and the bulk species. It is a very useful tool for simulation, for example, layer deposition. Well, so if you have a question, you can use the chat for me. Just write me on this. So, okay, let's return to the. Also, you may see the additional subtypes, like the current is given LCR, EM, LCR, VR. This subtype is concerned with current meant configuration. So generally, your discharge gap is in the series with the external electric circuit. And there are several possibilities for this external circuit. The first one, when you have a given current. So this case corresponds to the when the plasma gap connected in series with the current generator with the high internal resistance. The another simple case when the electric field is given. So, for example, for or somebody said you about how the electric field strength depends versus the time in your system, and you give this dependence in your simulation. Another, it's simulation with the given voltage and the resistance are very similar to the current given model. Well, one small model LCR, when we have connected in the net inductance, conductivity, conductance, and the resistance, and the plasma gap. So in the beginning, at the time equal 0, it is supposed that we have a charge inside of the capacitor, and there is some voltage. And after that, we have discharging of the capacitor and formation of the plasma in the discharge gap. And the last one is the ULCR circuit, when the plasma gap is connected in series with the resistor, capacitor, inductor, and voltage source. There is a possibility to give appropriate dependence of a voltage source versus the time. This is the main subtypes for the plasma models. As I said before, application of this model is strongly restricted by the 0D model. So we work in supporting with what we have uniform distribution in the system. But nevertheless, there is a possibility to simulate non-uniform system. And this possibility appears due to the flow sheet simulation. Let me demonstrate this one for the code where you get Chemical Workbench. Here. Okay. So you may connect different model, not only plasma model, but thermodynamic equilibrium model, kinetic model. You may connect all this model together and transfer data from the one model to the another. Sometimes this possibility is very, very useful. Let's demonstrate only one example here. For example, we have two electrodes, and streamer between them. So gas go in the space between this electron and treated by the plasma. We may regard this treatment that this treatment consists from the three principal phases. The first is a treatment by the streamer channel. After that, decaying of this channel and mixing of the species generated inside of the channel with surrounding gas. This is the axis, this is the time. And after that, let's say post-discharge pulse zone, when all electronically excited species are decayed, and we have a normal chemistry. After that, we have a second pulse, second streamer, and again decay and the chemical zone, and so step by step we have a treatment of the one specific volume of the gas. How is possible? It's strongly non-uniform system, but how is possible to simulate this system in rather rough manner, but nevertheless simulate to understand the chemistry which can be, for example, accelerated here. The streamer channel can be simulated through the plasma model. After that, the decaying and the mixing with surrounding gas can be simulated through the perfectly steered reactor, when we have a mixing of the species which were not treated by the plasma. After that, there is some mixing time. After that, the final zone when we have a normal chemistry can be simulated through the normal chemical reactor. Treatment by the second, third, and other pulses can be done through the looping of the whole simulation. The parameter here is the number of the loops, for example. It can be hundreds, thousands. Or another possibility, you may restrict simulation by the total energy input. For example, you know the total energy input 0.1 electron volt, and model will go around this reactor step by step after the achieving of this specific energy input. Okay, it's yes, it can be done, but of course, it's some approximation, and probably a rough approximation. Why? Because there are several non-self-consistent parameters which generally in the complete model can be calculated self-consistently, but here we need to know, for example, the ratio between the number of species which goes through the plasma channel and from the surrounding gas. How this ratio can be determined, for example, through the ratio of the total streamer volume divided by the total volume of the system, for example, a rough estimation. Another is the mixing time. The mixing time, the result of the simulation can be sensitive to the mixing time. And we need to know about this mixing time, and the mixing time can be, for example, estimated through the characteristic size of the streamer and the turbulent diffusion coefficient or something else like that. So flow sheet simulation bring us a very strong additional possibility to simulate not only a uniform system but non-uniform system also. Now about the data. You remember the second slide when we separated for the whole problem from the model and the data. Now we will move into the data. To simulate plasma chemical process, the number of the data very huge and much larger than in case of simulation of the normal chemistry, because for every species, chemical species, we should to take into account the interaction with the plasma, like the elastic, rotational, electronic, and many others. So the number of processes grows exponentially. Normally, generally, inside of the chemical workbench, for every calculation, we have a tree of the process. to help user to manage all process. There is a chemistry of the heavy particles. For example, let's go. Example maybe more interesting is the oxidation of the ethylene by the plasma. Okay, chemistry of the heavy particles class. There are too many reactions you see. Problem loading them. There is subclasses like the ion molecular reaction, equilibrium, non-equilibrium, energy exchange and collision of heavy particles. It means that, for example, relaxation of the excited nitrogen on oxygen, important process. Okay, you see, for every reaction there is parameters of the reaction. In this particular case, you see parameters in the Arrhenius form. I think it's possible to see this data in the table. And for the you see here like the graph. Okay. This reaction looks like the normal chemical reaction. What about the, for example, ionization? Let's look on the ionization processes we have here. For example, ionization of the ethylene. Here you see the parameters of the for the cross section presented through the GILO format. So it's very simple format. Left column is the energy, right column is the cross section. Okay. I think it's possible to see graph dependence. This is so this is a ionization cross section of the ethylene versus the energy in square Armstrong. Well, so too many information which necessary to perform calculation. Well, let's return. So, and question here, where this huge information can be found? So you see on this slide, this is a box. This is a representation of the Kinetech database, where we stored all necessary information for the thermodynamic and kinetic properties. Information can be delivered from the quantum chemistry, and there is a special interface which understands output of the quantum chemical program like the Gaussian, Games, and the Jaguar. Quantum chemical data can be transferred to the our database, and this data can be used by the Chimera code to calculate rate constant and cross section of elementary process. After that, this data can be delivered to the chemical kinetics program like our code Chemical Workbench or ChemKin. We have special code which permit to transfer between the two formats of our code and the ChemKin. So data generated inside of our database can be also delivered in the ChemKin format. This data can be also delivered to the Fluent, ANSYS, and StarCD, and another CFD code. About the structure of the database, let me better go to the code. Now we are going to the database. Well, need some connection to the server, to the database. We will see. Okay, so database consists from the several sections. The first section is the database of the thermodynamic properties. Second, oh, it's open. Oh, good. So the first is the thermodynamic properties. Second, the properties of the elementary process, and the most interesting, the database of the mechanism. The substances, you see its properties, thermodynamic properties of the substances. There is about 5,000 species here. And for the species, there are data in two types of the format. In format of the Institute of the High Temperature of the Russia and in the NASA format. There are two capability to use different type of the data. Well, okay. Database of the process, it's a collection of the all process, several thousand processes together, like plasma chemical and normal chemical process with all necessary information in terms of where this rate constant can be applied to temperature, region, pre-exponential factor, and other stuff, and different approximations starting from the Arrhenius and Troy and many others. Well, and most interesting is the database of the mechanism. This is a collection of the ready-to-use mechanism. We collect here many different mechanisms, starting from the well-known, for example, lead methane mechanism, combustion, GUI mechanism, together with our mechanism, which we elaborated in our company. For example, it's maybe most interesting for you. Plasma. Okay. It's thermal process. It's more interesting in the plasma assisted process. Just a second. No, discharge in the dry and humid air. For example, it's called thermal plasma, argon, plasma emission. Okay, it's not maybe so interesting. Discharge in argon and humid air. Okay. I'm looking for the mechanism of the methane and wait, here. This is a methane air plasma chemistry mechanism. Well, how how this database can be used? There is a three general way for the construction of the mechanism. One is just putting data by the hand in the calculation, for example, from external sources. Okay. For example, you may put additional reaction here and change parameters of the reaction just or cross section. It's the first way. Second way is the data export from the database of the elementary process. Okay, we have a lot of elementary processes in the database, but they are collected all together. And of course, we have automatic generation of the mechanism. So, for example, if you put like the initial species electron and the hydrogen, after the generator will give you additional species like the hydrogen ion. And also we'll try to find all processes between the electron and the hydrogen. And all this process together with the parameter will be collected together in the one mechanism. But responsibility for how this mechanism will describe correctly the process will be completely up on your side, because because some process is determined for some specific condition, for example, for low electron energy. Another reaction is determined for the high temperature region, but all reaction will be collected all together. And it's deal of the user to understand and to select appropriate reaction. So the more appropriate way here is the mechanism export from the database of the mechanism. It is possible. It is a very easy way. Just click on the mechanism folder here and found load from database. And here you will see all collection of the mechanism which we have inside of the database. Okay. Well, so we're not complete with the data, because what to do if there is no data? As I said, we have a special code here, Chimera. Chimera permits to calculate and estimate rate constant and cross-section of elementary process. Let me go to the Chimera. Here is a Chimera tool. It looks like very. This tool has a very simple interface. There is several examples. Like simplest one is, for example, ionization. User is just putting the reaction or process here. Choose the appropriate model and put all necessary parameters of the model. In the case of the ionization, it's necessary to put ionization potential of different shell of this particular tellurium atom and the number of the equivalent electrons. And Chimera tool permits to calculate not only cross-section and the rate constant. There is an example of calculation of cross-section for the tellurium in comparison with experimental data. Another important stuff here is the transfer property calculation. And when you are performing calculation with help of our plasma model, all necessary data together with the approximation of interaction potential between the different molecules and atoms. Here you see intersection correspond to the data for this particular interaction. In this particular case, it's interaction between the oxygen and the oxygen. And here is information about the potential interaction. Well, so all this information taken from the database and used during the discharge simulation. But nevertheless, you may go directly to the database and look for the properties and calculate transport properties. Here you see example calculation transport properties of the air for thermal conductivity, electroconductivity, viscosity. Solid line is the calculation with help of the Chimera, and different dotted and the figures correspond to the some calculation experimental work of well-known people like the Chris Straw, Capitelli, Miriam. Well, and let me to finish my lecture with two examples. Application of Chemical Workbench code. Actually, we have not so much time to discuss this example in the detail. I think this lecture is the first lecture in our series of lectures, and devoted mainly to the understanding what does it mean the chemical workbench and how it's possible to which model inside and how we may use this chemical workbench. The next lecture will be devoted to the particular case for plasma assisted combustion, for atomic layer deposition, maybe some other stuff. Here I will only just in very short manner describe two examples. The first example is a modeling of mercury-free line substance. The problem was the following. Is it possible to find some elements which can be replace mercury in the in the fluorescence lamp because the well, okay. Actually, there are no such element because all elements except of the mercury, uh, I mean the metals, have a very low vapor pressure. The idea was the following: let us use a halide of the metals. The vapor pressure of the halide is comparable with the vapor pressure of the mercury. So we may deliver the metal inside of the plasma zone. This is a tube of the discharge. Well, when we have evaporation, this is example for the gallium iodide case. After the evaporation, we have interaction of this molecule with the plasma. And normally, interaction with the electron will lead to the step-by-step formation of the metals. For the gallium iodide free, it's a three-step process. So we have a formation of the gallium, iodide, and iodide minus. Okay. So when we have a very high non-equilibrium concentration of the gallium, okay, just a second. Oh well. Okay. There is a question about is there something off with the reaction gallium plus electron with formation of gallium excited on the image charge. Which image you mean? Yes, of course. If probably here, let me turn to the presentation. Oh, how do we find my presentation? Good. Okay. Yes, of course. The electron is missing here. Yeah, sorry. Okay, so we need to add electron here. So when we have a non-equilibrium concentration of the gallium in the gas phase, there are two ways for the gallium. The first is again interaction with the electron and formation of excited gallium, which after that may emit photon. So we have formation of the light. The now way is the diffusion to the wall and condensation on the wall. So the question may be the following. This lamp will be worked up to the moment when the all gallium iodide free will be evaporated and treated. And we will have gallium, metallic gallium condensated on the wall. No, it is not right. Because together with the formation of the gallium, we have a formation of iodide. And iodide also diffuse to the surface. We have etching interaction of the first between the gallium and iodide, and again formation of the gallium iodide free. This is the idea for the new type of the fluorescent lamp. So the model was realized inside of the chemical workbench. Chemical mechanism for the gallium iodide free was elaborated. Very shortly, this mechanism consists from the following branches. The first is, as I said, direct interaction electron with the gallium and dissociation. Another way is dissociative attachment electron to the gallium iodide. And this process brings more gallium to the gas than the first one, because gallium iodide have a very high affinity for the electron. And the third important process is the formation of the gallium in the set of ion molecular reaction. So we have such mechanism: dissociation, ion molecular reaction, excitation by the electron, but in the end, nevertheless, condensation of the wall, etching, and returning to the gas phase. Here I try to show you example. This example in the chemical workbench. Yeah, here. Yeah. There is a mechanism. Okay. And the result, it's interesting to see for the result. This, for example, this is dependence of the electric field strength, mean energy of electron, and the mobility electron versus the time. Actually, we are looking for the steady state condition here. You see where mean electron energy is practically constant, and electric field strength is a constant on the level about 1 to about the 5 thousandths. Here we may see dependence of the principal concentration versus the time, logarithmic scale. We see formation of the gallium in the metastable state. This is the principal state of the gallium, and formation of the our electronically excited species like the excited gallium iodide and the excited gallium in the state 5s. Well, it is possible to look for the G factor. G factor is the number it show you efficiency of the excitation in this particular process. You see the largest efficiency, of course, concerned with the excitation of the gallium from the ground state to the first metastable state. The second level efficiency concerned with the excitation of the metastable state to the first radiated state, 5s. And here you see energy distribution function of electron for different times. The first time is very short. We see the distribution function are similar to the Maxwell one, and after that we observe the dropping of the distribution energy function with the time, and after the time about the 1 millisecond there is practically no difference between the form of the distribution function. So we have steady state regime. Let us know that jump of the distribution function in the area about the 5 electron volt is concerned with the losses of the electron energy for the excitation. Well, this is gallium iodide, and finally it's possible to make a parametric calculation. It's possible to change the pressure of the metric gas and the temperature, and to find the maximum efficiency of the system. For gallium iodide, the maximum efficiency on the level 50%. It's a quite huge efficiency, but lesser than the efficiency of the mercury. Sensitivity analysis permits us to understand which reaction are the principal here. So here you see the positive sensitivity means that this reaction is responsible for the increasing of the efficiency emission, and the negative responsible for the decreasing of the emission efficiency. As we expected, the principal input to the efficiency concerned with the dissociation of the gallium iodide and formation of the gallium in the metastable state and the ground state. Here. The negative largest input concerned with the diffusion of the gallium iodide to the wall, well, and the gallium to the wall. Practically, we have a loss of the emitter from the gas to the wall. This sensitivity analysis may permit us, for example, strongly simplify kinetic mechanism by selecting only important process. And finally, there is comparison between the atomic emission and molecular emission spectrum, comparison with the experiment, result published in this noted papers. Here the emission spectrum for the gallium iodide plasma. We observed a good coincidence between the simulation and experiment, but you may mention the principal feature of the system, that main radiation concerned with radiation of the atom. Input of the molecular radiation is about 1 order of magnitude lesser than emission of the atom. And the final example is the application of chemical workbench for modeling the plasma-assisted combustion. Here you may see solution of the following problem. We have some configuration of the nozzle in the turbine from our customer. And the nozzle roughly consists from the following section. There is two coaxial cylinders. When we have input of the air and the fuel, mixing between the air and the fuel in this zone, and together inside of this zone we have one electrode. The wall is sort of like the ground electrode. And we have a formation of nanosecond plasma here between the two electrons, between these two coaxial cylinders. So our treatment of the plasma has some afterglow zone, about 1 millisecond, and formation of the flame on the edge of the nozzle, and post-flame zone when we have a post-combustion zone. So we see that strongly non-uniform system, and again this system may be roughly calculated by the sequence of the models. The first model is the plasma model, when we are simulating interaction of the plasma with the gas. After that, plug flow model, which simulates propagation in the afterglow zone without plasma. When the combustion and the formation of the flame in this particular case was simulated by the perfectly stirred reactor. It is well known that perfectly stirred reactor may be used to understand understanding of the regime of the flame formation, when the flame has a steady form and when the flame have non-steady form. So this model is used for simulation of the flame area, and the post-combustion was simulated by the plug flow reactor. Well, so the first, this is the results comparison of with experiment of simulation of the circuit in the system. Here you see the simulation of the 1000 of the pulse, and here you see the profile for the every pulse, like the dependence of the discharge current versus the time. Interesting thing here that because the gas is treated by many pulses, the composition and properties of the gas change from one pulse to another pulse. We have accumulation of the excited species, we have accumulation of the chemically active intermediate species, and these species affect upon the discharge characteristic. And we have, and here we see how the discharge characteristic in this particular case, discharge currents, change from one pulse to another pulse. Green line is the first pulse, you see here. And after about the 100 pulses, we have a formation more or less steady state form of the pulse, blue line, and you may compare this blue line with the experimental point, it's a red dotted line. Well, but what for this simulation has been done? The principal idea is the following. Let us apply plasma to extend combustion limits. Actually, the nozzle and the turbine work in the lean condition region to avoid formation of NOx. And the purpose of the plasma extends this lean condition, stable region of the plasma or of the flame existence to the lesser values of the equivalent ratio. Here you see on the picture equivalent ratio versus the mixing time. This is characteristic of the well-stirred reactor. You may ask us about how you know about the mixing time. In this particular case, our customer provide us this number by the simulating of the detailed hydrodynamics in the nozzle. So we know about this time. It's about the 1 millisecond. Okay, so without plasma, there is the island, a blue island, correspond to the stable formation of the flame. And for the lean condition, the limit for the stable flame existence is 0.4. When after the application of the plasma with the following characteristic, like the 200,000, this island extend for the also for the lean condition up to the value about 0.3. This is essential for the turbine people, very essential. But what about another important stuff about NOx generation? Unfortunately, the picture is not so good as the previous one. Here on this slide you see dependence of NOx formation versus adiabatic temperature of the flame. Actually, this value strictly correlated with the stoichiometric ratio. Okay, so flame temperature can be regarded also as an axis for the stoichiometric ratio. Without plasma blue line, when we are working with the in the lean condition, it's a very good condition when the NOx concentration is very low and appropriate for using condition of the turbine. With an increasing of the stoichiometry and the adiabatic temperature, concentration of NOx grows very rapidly. What happens when we apply additionally plasma? In the high temperature region, the stoichiometric practically nothing, because the flame itself generates a lot of NOx. But in the lean condition, unfortunately, plasma, due to the non-equilibrium character, generates a lot of NOx, just because the electric field strength is so huge that provide not only formation of oxygen atom and accelerate chemistry, but also provide formation of the nitrogen atom. And this nitrogen atom react with the oxygen with the formation of NOx. This is bad news. Okay, but how we may accumulate our knowledge in terms of the optimization of the process? This picture, when we try to present possible optimization of the process, for the X axis is you see additional production of NOx in the system, and from the y-axis is changing of the temperature of adiabatic temperature. So it's a correlate with the changing of the stoichiometry. The higher this value, the more lean condition we may provide. Okay. So here you see experimental point is simulation result for the condition of 200,000. Also for the different energy input, 50, 100, and 240 joule per liter at the different pressure. You see the situation is rather bad because practically for all conditions the additional production of NOx is very huge. Okay, what happens if we will reduce electric field strength? Well, the situation became better because the lesser nitrogen atom produced. But together with the nitrogen, we reduce concentration of atomic oxygen. So we have a two effect, decreasing of NOx, but unfortunately, and decreasing of the plasma effect, the deviation of down temperature. But nevertheless, probably there is some good point if we will move into the lesser values of electric field strength, like the 80,000. Here we see, for example, for the energy input 100 joule per liter at the characteristic pressure of the turbine, enough strong effect upon the stability of the flame together with a low concentration of the additional NOx. That's practically all what I would like to represent you today. I think that this lecture was useful for you. Well, so please give question. I will glad to answer for your question. So we have about 5, maybe 10 minutes for answer of the questions. You have a special tools to write me here, like the chat, I suppose. Yeah, just open the chat folder and write me about the invitation. So we so this, you see it was a lecture is in the very, I'll say, obvious form when we have not enough possibility time to go deeper inside of the some particular process. Probably we shall organize the next several lectures which will be devoted especially for some specific application of the plasma and the possibility of simulation with help of a chemical workbench. I have a following question. I was wondering if there is a separate chemistry model for the chemical vapor deposition plasma. Chemical vapor deposition plasma system. Yes, there is such model. I will try to show you just in the window of the chemical workbench. Yeah, here. Oh my God. Here in the tree of the collection of our model, here you may see plasma and surface model. As I said, there is possibility for simulation of the plasma in the gas together with the chemistry both in the gas and on the first surface as well. So plasma deposition can be simulated, but I would like to stress it is 0D model. It means that the transport of the species generated by the plasma to the wall will be simulated in so-named effective radius approximation. So the diffusion flux to the wall will be determined like the diffusion coefficient divided by the radius of this effective radius. And reaction on the surface will be estimated in the accurate approximation using surface side formula. Well, so in this term, chemical workbench model will be similar to the Chemkin model because Chemkin has a very similar approach, but Chemkin cannot take into account correctly dependence of rate constant versus the electron energy distribution function. There is no solution of the Boltzmann equation. Well, I hope I answered on your question. Well, if you have a particular interest in the sum modeling, you may write us, and we may organize additional seminar devoted to your specific case of interest. Well, all our presentations, together with today's presentation, you can find on our website. They uploaded in both like the PowerPoint presentation and like the movie file. So please use it. Okay, guys, we have several minutes for the more questions. More detailed information about this particular case, which I described to you during my lecture, you may find in our papers, published papers. One of them you found here. It's devoted to the plasma-assisted combustion, and two papers concerning with the free mercury light sources simulation. Well, more questions. No. Yes. Sorry for my English. Yeah, there is a comment concerning with but I think my English is understandable. The question is the following. The emission efficiency on the graph with a nice picture is what light emission. Okay. This is a light emission. Так. Okay. I think we're speaking about this picture. What is light emission? So when we are spending plasma energy in the system, there are several possibilities for the losses of this energy. Let's say about the useful channel and unuseful channel. Useful channel is the formation of the excited gallium and in radiative state. Okay. Non-useful channel, all other channel like the elastic collision, dissociation, rotational collision, vibrational excitation, and all other. So emission efficiency of the system is a ratio of the all energy which goes to the formation of a radiative state, so it means the excited gallium, to the all energy which put it inside of the system. On this nice picture on the right side, you see a three-dimensional graph of this ratio. Okay, so I hope I answered for your question. More detailed information about how this calculation were performed with description of detail how the rate constant and cross section were calculated you found in the you found in the paper, this first one. There is a more detail about the particular application of the chemical workbench. Well, guys, I hope we close to the finish our lecture. So if there are no questions, okay, let us finish our lecture. Thank you very much that you found time to attend our lecture, and I hope see you again in on next our lecture, which will be devoted to the application chemical workbench for the plasma simulation, but with the detail for some particular system. If you have some specific demand for some specific lecture, please write us. We will try to organize such particular lecture. Thank you very much. Bye.